Friday is our next exam. It's all chapter 4 stuff. And a lot of chapter 4 is interconnected. So I do have a summary sheet I'm going to give you next week where it kind of ties together a lot of these ideas from chapter 4. Because I feel like a lot of these sections overlap. So when you summarize everything, it's more compact than section by section. And we still got 2 more things to talk about. 4.7 is a pretty abstract, you're not going to be that crazy about it, but it's change of basis because the notation is so ugly. 4.9 is Markov chains and application. It's a real nice application that I like a lot. And, so it'll be a relief, like it'll just be very down to earth. 4.8. And I don't even know, I'm sorry, 4.9. I don't even know what 4.8 is, I forget. So, whatever it is, we don't. And I just want to just take a moment to go back to this idea of rank, because it's a big issue in linear algebra. So if A is an n by n matrix, the rank of A plus the dimension of the null space of A is equal to n. N is the number of columns. And it's, when we broke that down, it's not that surprising. Now this rank of A, what is that thing? It's the dimension of the column space of A, which is the same thing as the dimension of the row space of A. So it's something deeper about a matrix, right? It isn't just about columns or just about rows. Because it involves both, it's given its own special name. For us, it's a little bit easier to get a handle on it, thinking of it as a dimension of the column space, because we work with that a lot. And then it's easy to see why the dimension of the column space plus the dimension of the null space has to add up to n. So this is the gist of the rank theorem, and that's important. And we're going to move on to something new. Start talking about change of basis. Question. Let me pull the screen down so we can see this a little easier. Now, basis of a vector space is a pretty abstract concept, and I feel like it can be really confusing when you get into the details and the theory, and the notation is also just sort of overwhelming. So what I wanted to do on this handout is just take a real specific example and draw some simple pictures to help you guys see the idea behind it. And something that just occurred to me this morning, I always want to think. It's very important to spend time thinking every day, so make sure you do that. Like, don't ever go through a day without thinking. So I'm lucky enough in life that I get to walk to work and think, and walk home and think. So these are all examples in R2, but it's kind of simple in R2. And so you wonder, why do I need all this machinery of linear algebra? And it's true if we were in a 2-dimensional or even a 3-dimensional world, we probably wouldn't need all of linear algebra. It's when you get into R100 or R1000, when you're dealing with these immense dimensions, which you often are in data science and in applications, where you just can't manipulate a few simple equations to get the answers, right? So having you're manipulating these giant matrices, and this theory really helps out because it cuts through a lot of the calculation steps. So that just occurred to me that it's kind of, it's not because of R2 that we have all this theory. It's because of much higher dimensional work. But still, we can draw pictures in R2. Okay, so what am I talking about here? So example in R2, standard basis, which I like to use the letter E, curly E, because it reminds me of these letters, E1 and E2 that we use for the standard basis vectors. I'm not sure if our textbook uses curly E. I can't remember if they even use that, but I will. And then in my picture here, this is just our standard coordinate grid. I didn't label the axes, but the squares are just 1, 2, 3, 4, going across 1, 2, 3, going up on the y-axis. So our basis vectors, 1, 0, and 0, 1, correspond to points on the grid, right? But we sometimes use arrows to represent those vectors, because the arrows help us think about what happens when we're adding vectors together. Now this is a pretty simple example, but my V is 5, 0, and I just want you to think about how 5, 0 is the same as 5 times the 1, 0 vector plus 0 times the 0, 1 vector, 5 times E1. With arrows, we can just say we go 1, 2, 3, 4, 5 copies of that E1 vector to give V. All right, now what I want to do in the next picture, so we're going to move up to the middle. This is the exact same graph grid, and I tried to copy it in a way where there's like a shadow of the original squares there. So it's the same graph grid. Here's the origin. Here's that same vector B down here. But now I'm going to think of a different basis of R2. I'm going to think of the bases B1 and B2. Now, B1 and B2 are better known as 2, 1 in their standard coordinates 1, 3. Again, that's just the point. 2, 1 from here, just go over 2, up 1. 1, 3, go over 1, up 3. All right? But to understand the meaning of that basis, you got to see the grid created in R2 by those two vectors, B1 and B2. So how did I get this grid? I just drew a line through the origin in B1. I drew a line through the origin in B2. And then I just drew parallel lines to those. And they're spaced out in a particular way. They're spread out by multiples of B1 in one direction, B2 in the other direction. And that parallelogram grid is really the grid of the coordinate system created by the bases B1 and B2. So like if you wanted to be different in life, you say, I'm not going to use old regular graph paper anymore. I'm going to use B1, B2 graph paper. I like parallelograms. I like diamonds. So you could do all your graphing with this coordinate system using that basis B1 and B2. Every point in the plane, so it's the same plane, same R2, has its standard basis coordinates, but also has its V1, V2 coordinates. So in V1, V2 coordinates, you know, the P1 is like a 1, 0 point. Throw an arrow out to there just to help it stand up. The V2 is kind of like our 0, 1 point. And if I want to describe my V, arrows can help us kind of imagine what its coordinates would be in this system, right? I can see I kind of want to take 1, 2, 3 copies of B1 and a negative 1 copy of B2. That's where this comes from. Notice that B is 3 B1 minus B2. So visually 1, 2, 3 minus 1 B2. So if you move parallel to B1 are copies of B1. Even though I'm way over here, I'm moving parallel to B2 in the opposite direction, that negative 1. And if you check out the coordinates add up. So under this basis, B1, B2 basis, we say the coordinates of V are 3, negative 1. I guess I'm going to write it on here, but just if I write 3, comma, negative 1 next to that vector V, I really got to know what basis that refers to. So in this course, we sometimes put that little curly B next to it, saying those are coordinates in that basis, right? So this point right up here would be what? 3, 0 in curly B. This point right here is, I think it's 1, 1 in curly B. I mean, we could go on and on and on. And really, every point in the plane has those curly B coordinates, not just the corners of the parallelograms. The corners of the parallelograms are just the contingent points. So, you know, I could do a 1/2 or a 1/3, and then I end up inside the parallelograms. There's no, there's no reason to have to prefer one basis over another. Of course, we're prejudiced. We love our standard basis. We've worked with it since we were young children. That's why we like it. But from a theoretical standpoint, there's no reason, again, not to suddenly say, okay, world, we're going to use this graph paper from now on with this basis, and this is how our coordinates are going to be set. Linear up, the vector space R2 doesn't care whether you use the standard basis or this B basis. Let's look at one more example, and then I just, same thing again. Now I have a C1 and a C2. Here are my C1 and C2 vectors in standard coordinates, right? -1, 3, and 1, 2. And that same vector B, exact same vector B, has C coordinates of -2, 3. So that same vector B is -2, 3 in C coordinates. And you can play around with the parallelograms there to see. And you may have already seen some algebra problems, and sometimes you may have seen this in calculus too, maybe in 110C, where making a change of basis sometimes, or a change of coordinates is what you would call it in calculus, makes a problem easier. It can make a really complicated equation an easier equation. If you have a funny ellipse shape that's rotated, sometimes choosing a rotated basis puts the ellipse in a simpler position in that system, and so problems are much easier to solve. So I think we can turn the page now. So my point then is just that there's this vector V that the standard basis is 5, 0. And basis B is 3, -1. And basis C is -2, 3. It has those 3 different coordinate descriptions of the same point, same vector, all right, in R2. So if we know the coordinates of a vector B for one basis, how do we determine the coordinates B for a different basis? How do we just easily get from here to here, or from here to here, or from here to here, right? And so on and so forth. And we're gonna kind of do it in a kind of back to basics way, where we just work with some algebraic equations, but then we're going to turn it into some matrix problems. So the working with just some basic equations is fine when you're in R2 and you don't have too many variables to deal with. The abstract theory will be much more useful when dealing in large dimensions, where you just get too many variables and too many equations to do it in our heads, sort of. Okay? So let's just read this over. So I'm about to turn this off. Suppose that for some vector W, suppose we know the B basis coordinates of W are -1, 2. How do we find the C basis coordinates? And we're still in R2, and B and C are the same bases of R2 described above. So what this is saying, we got to know how to interpret this notation, right? This notation right here is just saying the vector W is -1 times the B1 basis vector plus 2 times the B2 basis vector. I bet you could all solve this problem withow me saying anything. Because I think you can all see that if we could express B1 and B2 in terms of C1 and C2, same as previous page, then we just substitute into the above equation, and we'll get the C1, C2 coordinates of W. And that's what I want to do. I think it's worth doing. So I'm going to turn that off. That up. And so let's give ourselves a little bit more room. We'll take my rank. Switch it on here. And let's just sum up. I need some of this stuff on the board so I can work with it. So that B basis was 2, 1, 1, 3. So I'm calling those two vectors B1 and a B2. And my C basis was negative 1, 3. And 1, 2. So I'll call those C1 and C2, right? And what we know is that the B basis coordinates for W are negative 1, 2. Right? And what we want is what the C base, that's my attempt at an artistic looking C, the C basis coordinates of W are. It's given that W is negative 1 B1 plus 2 B2. That's what those B coordinates W are telling us. We want to express B1 and B2 in terms of C1, C2. Let's just say B1 is, I have to introduce some notation here. I'm going to say x1 C1 plus y1 C2. And B2 is equal to x2 C1 plus y2 C2. You won't have to come up with these x1, y1, x2. I know it's a little confusing looking at it this way. We want to solve for x1, y1, x2, y2. We got 4 scalars we're trying to find, right? And this is just a very straightforward kind of algebra problem. Let me recopy this in terms of coordinates. I guess I forgot to close my bracket right there. So B1 is 2, 1. X1, C1, negative 1, 3, plus Y1, C2 is 1, 2. x2, c2, or sorry, x2, c1, negative 1, 3, plus y2, c2 is 1, 2. So we can also express this as a matrix equation. 1, 3 equals negative 1, 3, 1, 2 times x2, y2. It's, again, this is so simple, it's almost easier to just work with the algebra and not even write the matrices down. So when we solve, I'm not going to write out the details of solving this. I get x1 is equal to negative 3/5. y1 is equal to 7/5. x2 is equal to 1/5. y2 is equal to 6/5. And those actually are unique solutions. The matrix that I wrote here, here we can see pretty easily that we have linearly independent columns, right? Because the two columns are not scalar multiples of each other. So the columns are linearly independent, the matrix is invertible. That means there's a unique solution to those systems, just one solution to both. Notice there were two systems to solve. That's going to help us think about things later. And so, okay, so what is W? W is negative 1 B1 plus 2 B2, which is negative 1. Now we can express what B1 is. B1 is negative 3/5 C1 plus 7/5 C2 plus 2B2. What is B2? B2 is going to be 1/5 C1 plus 6/5 C2. And we can multiply all that out finally. And surprising me, but it actually turns out to be 1 C1 plus 1 C2 when you add all those up, right? Because we get negative, or no, we get positive 3/5 C1 plus 2/5 C1 is 5/5 C1 is 1. And we get negative 7/5 plus 12/5 is 5/5, positive 5/5 again. So through the miracle of me having made up this problem, we end up with a 1. So that's, we want a fancier way of doing this, right? So this isn't the way we're going to keep doing it, but I wanted you to see you don't need to be Einstein to figure out this little bit of algebra here. So what do we have here? We can say W, use our fancy notation, C coordinates is 1, 1. So we started from the B basis coordinates for W, and we found the C basis coordinates for W. Just kind of notice that it took, we ended up with this matrix that looks a lot like just using these two columns. And we also had two systems that we were solving, right? Two little systems. And I want to just get the point of the handout again. did. The lights again, because we're going to look at this. All right, so just so here's our process in symbols. This is what we just did. So the point of that was to help keep this abstract notation from seeming so intimidating. This is how we can write things out in symbols. The c coordinates of W are the c coordinates of negative 1b1 plus 2b2. Okay? The coordinate mapping is a linear transformation. This assigning of c coordinates is a linear transformation, which means we can take apart a sum as the coordinates, c coordinates of each sum, and we can also factor out scalars from that assignment. Okay? So the c coordinates of W, this guy, has to be negative 1 times the c coordinates of B1 plus 2 times the c coordinates of B2. And if you just think about what we did, I mean, that's basically the calculation we're going through. Now, this can be thought of as a matrix times a column vector, right? Where these are the two columns. So the c coordinates of B1, c coordinates of B2 times negative 1, 2. And that was the calculation we went through, by the way, by hand. So we actually figured out what those were. So here are my fractions with fifths, right? These are the, these guys are the first column, and these two, 1/5, 6/5, are the second column in this way of expressing things. And sure enough, if I multiply this matrix times this column, there's my 1, 1 that we got right here, right? So just seeing that explained in that sort of notation, which means well, we're going to take the matrix up here, which had the c coordinates of B1 and B2 as columns, and we're going to give it a special name. This P with backwards arrow, C backwards arrow, B. And we got to get used to this notation. And we're trying to take this easy so I don't just throw it at you. The arrow goes backwards because we really are converting we're converting B basis coordinates to C basis coordinates by multiplication here, right? Because what did we do? We used that matrix to multiply the negative 1, 2. Those were B basis coordinates. And we ended up with C basis coordinates. We always multiply on the right. So because the action is going from right to left, the order of the B and the C and the arrow are really important. We put the B coordinates on this side, we multiply by that vector, and what pops out, what we get are C coordinates. Okay? That's called the change of coordinate matrix from B to C. The columns of this change of basis coordinates are the C coordinate vectors of the basis B. That is the B basis vectors expressed in C coordinates. So the challenge for you guys, you don't want to get the B and the C mixed up here. These are B basis vectors expressed in C coordinates. So these vectors expressed using those coordinates, not the other way around. Because if you get it backwards, it's backwards and it's wrong. Okay. And what you'll see, we'll have, the notation is actually going to help us keep this straight. So again, here's another explanation of how that notation works. I mean, it looks like it's so heavy it's going to fall right off the page, right? So we're going to read it from right to left here. We start out with our B coordinates of vector x, the B coordinate vector. We multiply by this matrix, and the product is going to turn out to be the C coordinates of that vector x. And again, notice how the notation is meant to help us, not confuse us. The B's match up here. The multiplying by the P matrix transforms us to the C coordinates. So if you just see that matrix, it's kind of telling you put the B coordinates on this side, you're going to end up with the C coordinates on that side. Right now, theorem. This wouldn't be life. So now we're just going to try to word this in generality where we're in n-dimensional space. So B and C are two bases of any n-dimensional vector space, V. There's a unique matrix denoted, however you want to read this thing, P over C backwards arrow V, such that any vector X in V fits into this equation. This is just recopying what I had up higher on the handout. And this is a key equation for you guys to understand here. The B coordinates times this change of coordinate matrix gives us the C coordinates of a vector. And to me, the tricky part is to remember that this matrix is the B basis vectors expressed in C coordinates. So the tricky thing here is you don't want to get this backwards. You don't want to say these are the C1 through Cn expressed in B coordinates, right? We got to try to keep that straight. And this motivation leading up to this is meant to help you believe this is really what makes sense to multiply the B coordinates by to get the C coordinates of a vector. There's something I want to say. Oh, good. What are the dimensions of the P matrix going to be? P is what by what? M by n? Anything by anything? It's always going to be square. It's always going to be square. Yeah, so I think that gets lost in the shuffle here a little bit. So the number of vectors in the B basis has to equal the number of vectors in the C basis, because we now know if we have an n-dimensional vector space, all bases have the same number of vectors. So if the dimension is n, any basis has n vectors. And so if this is transforming a basis of n coordinates to a basis of n coordinates, this is always going to be an n by n matrix. So that P matrix is always square. N by n, where n is the dimension of vector space. Proving this theorem actually is really just like what's on the board underneath here, even though that was a very specific example. So we're not going to go through the steps of a proof, but in an abstract argument, you're just with a lot of dots and ends, you go through the same kind of reasoning that we went through underneath here. And then we're not going to do that. Again, we did our motivating example was enough. But there's more. We still have another problem we're running to get to here. So what's the there's more all about? So the proof is over. Don't worry about the proof for that. The more is important. So since the B1 through Bn, that's a basis, so they're certainly linearly independent vectors, so are the B1 through Bn expressed in C coordinates. So the matrix that has those columns, since the columns are linearly independent, the P matrix is invertible. It's an n by n invertible matrix. So take this equation that I've already written down several times, multiply both sides on the left by, unfortunately, the hole punch kind of got at our handout here. That's just minus one that's inverse. So that's the P over C backwards arrow B inverse. That's all I'm trying to say. The inverse of that P matrix is just getting burdened with even more notation. And so what happens? here we're multiplying on both sides. Basically, these guys are going to cancel out because that's matrix times its inverse. We're just left with the b coordinates of x. Here's the inverse on the left-hand side of the c coordinates of x. Well, we can reinterpret this equation. What this inverse matrix is doing, it's just converting the c coordinates to the b coordinates. This isn't very exciting. We would have expected this to happen, I think. In other words, the inverse of this P matrix that converts B coordinates to C coordinates is the matrix that converts C coordinates back to B coordinates, which is sort of just like what we want, right? The inverse of that, we'd like to do the reverse operation. So this is an important relationship for you guys to know, all right? Now, this exercise is, I'm not going to rush it because we're good with the time with this chapter, so we may just start this because this is something you got to know how to do for our test coming up. So here's R2 with two bases. I don't think these are the same. I think I've made up new ones, right? Yeah. So new B, new C. So I'm getting new mileage out of those letters, right? We're going to use B and C a lot when we talk about two bases. So this has no relationship to our original B and C. But here's a new basis B. Here's a new basis C. Because we need to come up with some different numbers. We just keep getting the same numbers. So I want you to find the change of coordinate matrix from B to C and the change of coordinate matrix from C to B. And before I turn the projector off, I'm going to write down what I'm supposed to do. So in A, we want to find the change of coordinate matrix from B to C. I should just a good test question would be, can you even write down what that is, right? Can you write down the notation? It's a P, and I kind of silly, but not that silly. If we're changing from B to C, you got to get used to the B goes on this side, the arrow goes that way, the C goes there. The change of coordinate matrix from C to B is going to look like this, that, like that. Right? And as you start working with this, you'll say, oh, that makes so much sense to write it in that way. These are related to each other. One is the inverse of the other. So right away, you should realize that if I can just find one of them, I just then compute the inverse matrix, and I got the other one. So there's like one new calculation here. Step B is just find the inverse of the matrix we found in step A, right? So this is just inverse of the answer in part A. But this is a new process. I can fit it over here. And it's not too bad once you see what we're going to do. Let's see, we got a minute. So before I turn our projector off, what we're going to do is we're going to use a special kind of augmented matrix to solve this problem. So what I'm going to do is I'm going to set up a new kind of matrix where I'm going to put the C1 and C2 vectors on the left. So that's what, 0, 2, 1, 1. So that's C1 and C2. And then right up next to it, I'm going to write the B1 and B2 vectors. So 3, negative 2, negative 1, 2, B1, B2. And if you want, if it makes you feel better, you can do a little dotted line down the middle. Sometimes people do that. It's not necessary. But it is, we are thinking of these as two separate pieces of this special kind of augmented. It's like doubly augmented. Instead of having just one B column, we're actually putting two B columns in a sense on the end of it. And what all we're going to do is this. know how to do it. We're going to take row operations, and we're going to convert this to, we're going to get an identity matrix in the first two columns. So it's kind of like that process of finding an inverse, right? But also kind of not. And what we're going to end up with is this P matrix. And notice how, here's where the notation is meant to help us out. Like you're like, how am I going to keep this straight? How am I going to get the B's and the C's in the right place? Notice that we put our C basis here, our B basis here in the original augmented matrix. The change of basis matrix that we end up with will have the B basis here and the C basis here. And our arrow always goes that way, right? So that's not really a choice. So our notation fits in very nice with this method. And pull out our results here. So you can fill in the steps. I got to 1, 0, 0, 1, negative 5 halves, 3, 3 halves, negative 1. Just through row operations, right? So I row reduced. And we should all get the same thing. So pluck off those last two columns. It's very anticlimactic, you know. Hardest part is writing your curly B's and curly C's. So this matrix just halves, 3, 3 halves, negative 1. What does this thing mean? If I took B coordinates for a vector, so we're in R2, so just two components, and multiplied by this matrix, so with the B coordinates on the right, I'm going to end up with the C basis coordinates. So it sort of automatically goes through. Really, we just did, well, I didn't do it because I didn't fill in the steps. It only takes a few row reduction steps. You're doing the algebra that we did that's under discrete on our warm-up problem. It just takes you through all that process automatically. Still got a couple minutes.
5 minutes.
Oh, 5 minutes, yeah. So that's our answer to A. And to find B, we just need the inverse matrix. So find the inverse. So I would take this negative 5 halves, 3 halves, negative 1 as the first two columns of a matrix with now the identity, right? 1, 0, 0, 1 here. And row reduce to get the identity matrix in the first two columns. Or really any process you know to find the inverse of this matrix to be applied. This is sort of our favorite process, I think, to find an inverse. And I get 1/2, 3/4, 3 halves, 5/4. And so far in the corner, back to the other side. So that's actually my answer for part B, right? And it kind of makes sense if you multiply these two together, you get the identity matrix. So if you take if you want to convert from B coordinates to C coordinates back to B coordinates. You're just going from B coordinates to B coordinates, which means you should just leave your coordinates alone, which is what the identity is. Let's see, our other one was negative 5 halves, 3 halves, and 1. So, good potential test problem. Alright, so I just want to, oops, yeah, I think we got time to talk about this. You know, it seems like this weird thing, this special augmented matrix that we're setting up right here, and it's not. It's like something we know so well. So why does this work? Here's my B basis. Here's my C basis. We're trying to find this guy, right? That's what the answer to A is. This column vector will have entries x1, y1 according to this equation, just like what we did on the, again, at the beginning of class. B2, we're looking really for the x2, y2 values for the second column. So just like underneath the screen, we had two systems of equations. Remember, this is a matrix times a column vector, matrix times a column vector. When we could have solved each of those separately. In other words, we could have written this down as two separate matrix equation problems. But what we're doing, where there's a B column here and a B column here, but because we're doing exactly the same steps, we combine these two systems into a single calculation. So we just, again, leave the same C1, C2, but we do the augmented B1 and the augmented B2 system at the same time. And if we had done them separately, what we end up with is the solution to the first system in this column and the solution to the second system in this column, which is what we want. Okay. So to me, it's just a case of solving two matrix equations at the same time here with B1 and B2. If you had three vectors, if you were in R3, you would just do three systems at the same time, or four systems